Okay, here we are back again. We're just going to continue on with our nomenclature. This time we're going to talk a little bit about when we have nonmetals bonding together. You'll recall that at one earlier in the lessons I suggested to you that you have a chart or a question tree to decide what system you're going to use to name compounds. And when we start with the compounds, if we ask, is the compound ionic or covalent? It's ionic if it's metal and nonmetal. It's covalent if it's nonmetal. All right? And we've done this side of the decision tree. We haven't done the other side. Well, how do two nonmetals form compounds? Well, you've probably learned in grade 9 and grade 10 that this is where we find the covalent bond. Okay? Covalent bonds. So elements with 3 or fewer valence electrons generally, well, what do? They tend to lose electrons, okay, to form stable octet. Elements with 5, 6, or 7 valence electrons generally gain to form a stable octet. And so ionic bonds are generally these things, some that lose, some that gain. We have an electrostatic attraction. But what do elements do when they don't have metals to bond with? Well, they're going to have to share electrons in order to form that stable octet. Now, in this middle paragraph, I've given you the actual definition of what a molecule is. And I would really like you to take that to heart because a lot of students use the term incorrectly. Electrically neutral combinations of nonmetals in fixed ratios are called molecules. That's the only time you use that term. You never use it in an ionic bond. Because they are really just ratios between ions. This is where Lewis diagrams can come in useful. We're not going to spend a lot of time this year on Lewis diagrams, more next year, but we can use these things in order to figure out what is the actual formula of a compound when they combine. Okay, so when atoms combine by sharing electrons, that's called a covalent bond. And the potential energy is reduced, thus making the addition of the two more favorable than the atoms separately. We won't get into that quite yet. The energy decreases, therefore, do you remember what that is? If the energy decreases, it must be giving off energy. That's an exothermic process. And we'll just introduce that now. Energy appears as heat. Further examples? Well, we're not going to, I think we'll just forego that right now. And predicting bond type, again, what we're going to do here at the bottom of the page, when you have a metal and a nonmetal, you're just going to choose that as being an ionic bond, and a nonmetal, we're going to call it a covalent bond. And this will work for just about everything we're going to do. Okay, turning the page to page 73. I've asked the question, are all bonds created equal? And the answer is basically no. And this is where we're going to introduce our fourth periodic property. And that periodic property is something called the electronegativity. Now, it's kind of an interesting process, this electronegativity. It was developed by a fellow by the name of Linus Pauling, who won 2 Nobel Prizes, one for his nature of the chemical bond, and one was, I believe, a Peace Prize. I think at one time he was the only individual to win 2 Nobel Prizes. I think groups have won 2, but I think he's anyway, I don't know if that's absolutely true, but anyway. Anyway, different countries use different scales. I think there's a Russian scale and that kind of thing, but they basically all do the same thing. And what is electronegativity? Well, basically, it's the relative attraction that an atom has for electrons found in a covalent bond. And I use the example HF. If we look at HF, we know that hydrogen has 1 valence electron, fluorine has 2. I'm going to represent the fluorine valence electrons. Sorry, it doesn't have 2, it has 7, using crosses. And the hydrogen electron is indicated by a circle here. So there's our Lewis diagram for HF. Well, we're really interested in what's going on here. And with certain atoms, we see that they can attract pairs of electrons found in a bond better than others. And if we look at the electronegativity of fluorine, we'll see that actually it has the highest electronegativity of all elements on the periodic table. Now here's my analogy. I kind of look at it like there's two houses side by side, and each has a child, okay? And each has a child, and these children like to play together in their backyards. And so the one child will have to go over to the other child's house to play. And one backyard has all kinds of toys and swings and play sets and stuff like that. And the other house doesn't really have anything. As a matter of fact, it's got a dog that sort of leaves behind all kinds of surprises. And it's just not fun backyard to play in because, you just don't want to step in any of that. So if we took a snapshot at various times during the day, we would see that the two children would probably be in one backyard more than they would be in the other. Does that mean there's been a complete transfer? No. Well, the other child goes back to his or her house later on in the day, but we see that the two children stay in one house more than the other. Well, electrons are somewhat the same way. Fluorine right now is the attractive backyard, and so these electrons tend to spend more time in the vicinity of the fluoride than it does from the hydrogen. Okay, there's a number of different ways that we could indicate that. Sometimes, because this is not a complete charge, we use the lowercase delta and say that this end of the molecule is a delta negative and this one's a delta positive. Sometimes you use a little symbol that looks like this with an arrow indicating that the electrons have gone in the direction of the fluorine. And we would say that this is a polar bond. Polar because we've created two poles, a positive and a negative. So it's a polar bond. These bonds, we're going to study the effects of these bonds on molecules in the grade 12 year. And so look out for that next year. And when we look at bonding, if we look very carefully at bonding, we can see that there's a bit of a bonding continuum, okay, between polar and nonpolar. Well, how do we determine it? Well, you need to use something called the electronegativity, which we've defined up here. And we see that the electronegativity for fluorine is a value, let's say it's around 4.0, and for hydrogen, it's about, 2.1, 2.2, something like that. Okay, so our change in electronegativity, our delta En, is about 1.8. This is quite a high value, okay? And it says that the one with the higher electronegativity has the electrons moving towards it. So it is the delta negative, and this is the delta positive. So that's electronegativity. And how would you get a change in electronegativity of 0? Well, there's two ways. We either have two elements with roughly the same electronegativity, so when we subtract one from the other we get 0, or we could have two elements with exactly the same electronegativity because they're the same element. If we looked at oxygen, for instance, oxygen forms a double bond. Here's its Lewis diagram. Well, obviously, if I subtract the electronegativity of oxygen from the electronegativity of oxygen, I will get 0. So we would call that something that would be 0 if our change in electronegativity is, just make sure I'm on the page here, En. If it's 0, that means we have a pure covalent bond. Okay, and if we have a change in electronegativity, then we would have a polar covalent bond. And if we have a really big change in electronegativity, then we would have something called an ionic bond. Okay, so now some books will suggest that a change of electronegativity in the neighborhood of 1.7 is an ionic bond, but we're not going to do that. We're going to define an ionic bond as something between, can you remember, metal and non-metal. Okay, as soon as you see that, just call it ionic bond. If it's non-metal, and we have a change in electronegativity, we have a polar covalent bond. And it just varies in its polarity the bigger the value, the more polar the bond. Okay, we're not going to say anything much more about polar bonds than that this year. I did give you a little bit of a table here. You can see some of the effects of polar bonds, but again, it's a little more difficult to get into. There's a little bit more to it than what I suggest here. Here we have 3 compounds with roughly the same molecular mass. You would think that they're going to have roughly the same boiling point. Well, if we look at NO, which has a polar covalent bond, you'll see that the boiling point is quite a bit higher. Remember, this is a negative number. So it's quite a bit higher than the 2 with non-polar bonds. Okay, and that's a consequence, and we'll study that consequence next year. Okay. Anyway, I think that's as far as we're going to go with our dipole. Okay, and we'll stop there.